Hello guys, any questions from the previous lectures? Please have a look at the correct answer from the last test for the last test. A lot of you didn't get it right, so please discuss this with your seminars professor. Okay, let's continue. Today's topic is continuous functions. Continuous functions. Definition. Before the definition, let me say that throughout today's lecture, let function f of x be defined in some deleted neighborhood of x0 throughout today's lecture. Definition. A function f of x is called continuous at point x0 if there exists a limit as x tends to x0 and this limit equals f of x0. So the limit of the function equals the value of the function at this point. Examples. A function f of x that is just a constant is a continuous function. You can easily see that there exists this limit and it equals the same constant. F of x equals x is also a continuous function. You can check it yourself. Another one was f of x equals sine x. So you can do this as an exercise, or maybe we'll do this on the seminars. Okay. Definition. If a function is not continuous, at a point x0, then this point is called a point of discontinuity. of f of x, or simply a discontinuity. Okay, so let's write the definition of x0 being a point of continuity, so function being continuous, and x0 being not being a point of continuity. So x0 is a point of continuity. So I'm just writing the definition of the limit of my function. For any epsilon, there exists delta, such that for any x from deleted delta neighborhood of x0, it follows that f of x is from epsilon neighborhood of f of x0. This is just the definition of a limit of my function. Specifically for this case, we can write it a bit differently. This is exactly the same statement as for any epsilon there exists delta, such that for any x, look, here it says that x should be from deleted neighborhood of x0. But what happens if x equals x0? What happens here if x equals x0? The exact value of f of x0. Yes. So it definitely lays inside this neighborhood. So this is definitely true if x equals x0. So in this case, I can relax this restriction. I don't really need it. So I can write that x is just from delta neighborhood, or as an inequality x minus x0 less than delta, which is the same as x being from not deleted delta neighborhood of x0. Same statement. Okay, it follows, and this expression I will also write as an inequality. F of x minus f of x0, absolute value less than epsilon. Okay, so this is x0 being a point of continuity. So function is continuous at this point. Now let's write x0 is not a point of continuity. Actually, let me write it a bit differently. Let's write that x0 is a point of discontinuity. Since I call it that way. So I'm just negating this statement. So this statement is not true. There exists epsilon such that for any delta there exists x. Once again, I could have written that x is from deleted delta neighborhood, but I really don't need it. So I'm writing x is from just neighborhood. So x minus x0 absolute value less than delta. Such that f of x minus f of x0 absolute value is greater or equal than epsilon. Okay, so this is a point of continuity, this is a point of discontinuity. Very well, any questions? Let's see some examples. Let's look at this function sin x. This function is positive 1 if x is positive, 0 if x equals 0, and negative 1 if x is negative. So I'm going to show that this function is not continuous at point 0. So 0 is a discontinuity of this function. Let me draw a graph of this function. This function looks like this, like that, like that. So this is minus 1, this is plus 1. Geometrically speaking, it is like easy enough to see why we call it a point of discontinuity. I cannot draw a graph of this function without jumping from here to here. I cannot like continuously draw this line. Okay, so let's see. I'm checking if the definition of a discontinuity holds, the last line from the previous page. Okay, so there exists epsilon greater than 0. I shall write the exact number here. So instead of just greater than 0, let me write epsilon equals 1/2, which is greater than 0. Such that for any delta greater than 0, there exists x such that x minus 0. Let me reiterate that I am writing that 0 is a point of discontinuity. X minus 0 less than epsilon, less than delta, such that sin x minus sin 0 absolute value equals. So I say that there should exist such x. So I should provide such a number. I'm given providing such a number. So let x be just delta divided by 2. This is a positive number, so let me draw it over here. So this is this neighborhood, delta neighborhood of 0, from minus delta to plus delta. I'm just taking some number from this neighborhood. For example, this number. This would be my x. Equals delta divided by 2, which is a positive number. Since this is a positive number, sin x is plus 1. from the definition. So at this point, my function attains the value +1. So sine x equals just +1 minus sine 0 by definition is 0, which is 1, which is greater or equal than 1/2, which is epsilon. So I checked by definition that function sine x is not continuous at point 0. Any questions? Okay, moving on. Definition. Let x0 be a point of discontinuity of function f of x, and also let there be a limit of my function as x tends to x0. This limit is a finite number, real number. So this is a point of discontinuity, but there exists a limit. Basically, this means that either the function is not defined at this point, or the function is defined but has a different value from the limit. Then x0 is called a removable discontinuity. Since we can remove this discontinuity by changing the value of my function at one point, I can fix it by changing just one point. Example. Let's look at a function sine x absolute value. So this will be my function of x. So this function is 0 if x equals 0, and sine x was either +1 or -1 in other points. So absolute value is just +1 if x is not 0. So this is my function. And the graph of this function looks like this. Looks like this. Okay, so we can easily enough see that this is a point of discontinuity. I can use exactly the same proof. Look over here. No. Over here. Exactly the same proof I used here. I took a positive number, and the value at this number is +1, and so this difference is greater than 1/2. I can use exactly the same proof over here to prove that this is a discontinuity. Okay, but now we can see that there exists a limit of my function as x tends to 0, and this limit is of course just +1. I think you can do it easily enough yourself just by observing that in a deleted delta neighborhood of 0, any point but 0 itself, the value of my function equals 1. So just by definition of the limit, this limit equals 1. Very well. So this is the case. This is a removable discontinuity. The function has a limit, but is not continuous. We can fix it by changing just one point. So if I change my function from being 0 to being 1 at x equals 0, this function will become a continuous function. Removable discontinuity. Definition. A point x0, a point of discontinuity, of x is called a discontinuity of the first kind if there exist one-sided limits at this point. One-sided limits at this point. So that would be f there exists f of x0 plus or minus 0. And I remind you that when I said that the limit exists, I mean it exists as a finite number, a real number. Okay, let's look again at this example. You can see that there does exist one-sided limit left one equals minus 1 and right one equals plus 1. So this is a discontinuity of the first kind. Also, let's look at this function. Here also both one-sided limits exist, then they just happen to be equal to each other. So if this limit exists, then one-sided limits also exist and are equal to each other. So a removable discontinuity is definitely a discontinuity of the first kind, one of the cases. Okay, moving on. Definition. A point x0 is called a discontinuity of the second kind if at least one of the one-sided limits does not exist. Let me write it down. does not exist. And once again, when I say the limit exists, I mean a finite number. So does not exist could mean that the limit equals infinity. Examples. F of x equals 1 over x. So this function. At point 0, it has one-sided limits and they are infinities. So finite limits does not exist. Finite limits do not exist. Let's also look at this function. F of x equals sine 1 over x. You should have discussed this function on the seminars. So let me try to draw it. So this is right half of the graph and the left half is the same, of course. And during seminars you should have discussed that this function does not have a limit at point 0 and specifically does not have any of the one-sided limits. Even though this function is finite, so this is not infinity, there just isn't a limit. Okay. Another example, which you also should have discussed during seminars, is the Dirichlet function. D of x equals 1 if x is rational and 0 if x is not rational. Guys from the other group, from the Vera Markasheva's group, did you discuss this on the seminars? I think this is just you here. Did you discuss this function on the seminars? No. Okay, please ask her to discuss it next time. Okay, this function, Dirichlet function. This is one of the problems from the homework, so you should do this anyway. So please remind you. Okay, basically in just a couple of words. So we have everywhere dense set of rational numbers. So in any neighborhood of any point there is a rational number. So everywhere dense we have these points where the function equals 1. But also the same is true for where the function equals -1. I hope it can be seen. It probably cannot be seen. Let me do it like this. Is it better? Possibly. Okay, so this function is also discontinuous and has a discontinuity of the second kind. The interesting part about this function is that it is discontinuous at every point. Unlike those functions that we are familiar with, this function is discontinuous at every point, which is kind of interesting. functions continuous at a point. So functions continuous at a point. Theorem. Let a function f of x be continuous at a point x0 then there exists a neighborhood of x0 such that my function is bounded in this neighborhood. Okay, let's continue. Before we do, I have an announcement. So next Monday I can't give you lectures, so instead we'll have it this Saturday. So 25th of December, this Saturday. First class, I think. So at 9 o'clock starts the lecture. I don't remember the room. Okay, I don't remember the room, but I will send it to you by email, or maybe Maria Kaplina will send it. And also the same happens with the 10th of January. So instead we'll have a lecture on 15th of January. Okay? I'll send it to you by email. Okay, moving on. Proving this. Хорошо. Okay. Very easy. So the function is continuous at this point. So let's write this definition of continuity. For any epsilon greater than 0, there exists delta such that for any x from not deleted delta neighborhood of x0, it follows that f of x is from not deleted epsilon neighborhood of f of x0. Now, it is true for any epsilon. Let me choose some number epsilon. For example, let epsilon be equal to 1. For example. Then there exists a number delta such that for any x from this neighborhood, it follows. And this statement I will write as an inequality. So f of x0 minus 1 less than f of x less than f of x0 plus 1. But this basically means that this neighborhood of x0 is such that function f of x is bounded above by this number and bounded below by this number. So this is the neighborhood in question. So f of x is bounded in this delta neighborhood of x0. End of proof. Theorem. Проще сделать. Let a function f of x be continuous at a point x0, and also let f of x0 be not 0, so either a positive or a negative number. Then there exists a neighborhood of x0 such that how do I phrase it? At any point of this neighborhood, my function f of x has the same sign as f of x0. Basically, this means that if my function at this point x0 was positive, then it stays positive in some neighborhood. And it was a negative value, this negative value was negative, then it stays negative in some neighborhood. Okay, let's prove it. Easy enough. Proof. Once again, I write down the definition. Let f of x0 be positive, for simplicity. I write down the definition of continuity. For any epsilon, there exists delta, such that for any x from delta neighborhood of x0, it follows that f of x is from epsilon neighborhood of f of x0. So, f of x0 is a positive number, so I can choose epsilon be 1/2 of f of x0. This is a positive number. For this epsilon, there exists delta, such that for any x from delta neighborhood of x0, it follows that f of x is less than f of x0 plus epsilon greater than f of x0 minus epsilon. F of x0 plus epsilon is 1 plus 1/2 times f of x 0. So this would be 3 by 2 f of x 0. And this value is 1 minus 1/2. So this would be 1 by 2 f of x 0. So I care about this part of the inequality. So for any x from this neighborhood of x 0, it follows that f of x is greater than 1/2 f of x 0, which is, I don't need this, which is greater than 0, since f of x 0 was positive. So I have found a neighborhood such that in this neighborhood f of x attains only positive values. F of x is positive. End of proof. Similarly, of course, we can prove that the same statement holds for negative value over here. Any questions? I think I should write it. Proof is similar if f of x 0 is negative. End of proof. Yeah. Oh. Last line one more time. Okay. So, in this neighborhood, I have shown that f of x, for any x from this neighborhood, f of x is greater than 1/2 f of x 0. And we know that f of x 0 is a positive number, so f of x is greater than 0. Maybe I can draw a picture. I think it would work here nice enough. So, suppose this is my function. This is point x 0, and my function is continuous at this point. This point is f of x 0. This is a positive number. I'm choosing epsilon equals 1/2 f of x 0 basically to ensure that this epsilon neighborhood of f of x 0 stays positive. So this is f of x 0 minus epsilon, f of x 0 plus epsilon. I'm choosing small enough neighborhood such that all numbers here are positive. And for this epsilon neighborhood, by definition of the limit, I can find delta neighborhood of x 0 such that for any x from this neighborhood, we'll basically have this part of my graph. Like that. It stays inside this corridor. So greater than this value, smaller than this value. And the important part is that this function stays greater than this value, which is a positive number. Okay, theorem. Let functions f and g be continuous at a point x0, then f plus g is continuous. Let's call it A. F plus g is continuous. At x0, B, f times g is continuous, and C, if g of x0 is not 0, then f divided by g is continuous. At x0. So the sum, the product, and the quotient of continuous functions are continuous functions. This, of course, just to ensure that I do not have 0 in the denominator. Proof is very easy. Just apply the arithmetic properties of limits to those cases. To be clear, this is not a proof, this is idea of a proof. This is not a proof. I hope you can do it yourself. You should be able to do this yourself. Theorem. Let a function f of x be continuous at x0. Also let f of x0 be y0. Let's call it y0. Let a function g of x be continuous at y0, this point. Then the composite function let's call it not function g of x, let's call it a function g of y. G of y. Since it attains value of y0, let's call it g of y. It does really matter, of course. Then the composite function g of f of x is continuous at x0. Как я там эту штуку называл? Никак, да? Idea of a proof. Apply the theorem about the limit of the composite function g of f of x. I don't think I called this theorem any specific name, but I hope you understand what theorem I refer to. This is a limit of a composite function. Apply the theorem about a limit of a composite function. I hope it would be easy enough for you. Так, очень много времени. Okay, using those theorems, we can, for example, let me write over here, example, any polynomial p of x equals an x power n plus an minus 1 x power n minus 1 plus and so on plus a1 x plus a0 is continuous. Proof. We mentioned it before, we can easily enough check that a function x, f of x equals x, is continuous by applying the product rule from the one of the previous theorems. We can prove that x power anything is continuous function, x power 2, x power 3 is continuous function. No, not clear? Clear, okay. And hence, by applying a, what was this, a summation rule, we can see that sum of those continuous functions is a continuous function. Okay. Okay, any questions? Any questions? Guys, is everything clear? Moving on. Definition. Let a function f of x be defined on a closed interval in AB Let's start with an open interval. Let's have an open interval first. Let a function be defined on an open interval AB. Let for any point x 0 from this interval AB f of x be continuous at this point. Let's write it differently. So limit as x tends to x0 f of x equals f of x0. So at any point on this interval, my function is continuous at this point. Then the function f of x is called continuous on an open interval AB. So, if we have an open interval and my function is continuous at every point of this interval, then the function is continuous on this interval. This is the definition. Okay, definition. It's a bit different on a closed interval. So let a function f of x be defined on a closed interval Now, this closed interval, it contains this like similar open interval if we exclude the endpoints. So the first thing I'm going to demand that this function is continuous on this open interval. So I'm copying this line. Let for any x 0 from AB x tends to x0 f of x equals f of x0. So this was the same as the previous line. But this is only about the inner points about this closed interval. What about the endpoints? Let limit as x tends to a plus 0 f of x equals f of a. So on the left side of the intervals, I want the right limit to be equal to the value of the function. And also on the right side of the interval, I want the left limit to be equal to the value at this point. Okay. Then the function f of x is called continuous on a closed interval. So this is function being continuous on a closed interval. Okay, any questions so far? Is it still good? Sound? Okay. Any questions so far? Okay, we will have time to formulate but not prove the next theorem. Theorem. It will be called Balzana Cauchy intermediate value theorem. If a function that is continuous on a closed interval so a function continuous on a closed interval assumes values with different signs at the endpoints of the interval then there exists a point in the interval where it assumes the value 0. So, this is a picture. So, I have a continuous on a closed interval from a to b function, and this function assumes negative value f of a on this left side of the interval and positive value f of b on the right side. So there should be a point somewhere here when this function assumes value 0. Basically, it means it intersects the x-axis. This seems very obvious geometrically speaking, and the rigorous proof we will discuss next time. Okay, if you don't have any questions, then thank you for your attention. See you on Saturday.